right, so next we're going to look at our central limit theorem. So our central limit theorem, again, should look familiar. It's something that we saw in Chapter 7. If certain conditions are met, the central limit theorem assures us that the distribution of the sample means follows an approximately normal distribution, no matter what shape of the population distribution. And this goes along with those images that we just saw. We can take a multimodal skewed distribution for a population, and then we can take samples, and based on those samples, we can get something that's closer or approximately a normal distribution. If the population is normal to begin with, then the sampling distribution is exactly a normal distribution, regardless of the sample size. So if we start with something that we know is a normal distribution, it just makes our life easier because we know our sample is also going to be normal. If our population is not normal, then the larger the sample size, the better the approximation. All right, so our central limit theorem, if the following conditions are met, right, the sample is random and independent. Right? That eliminates our bias. Again, the first condition that we saw in previous chapters. That we have a large enough sample. Instead of doing a multiplication to test like we did back in Chapter 7, we're going to say that either the population distribution itself is normal or the sample size is large. And we're just going to designate a number of 25. As long as we have a sample size that it's at least 25, we're going to say that that is large enough. Our population must be large enough. So our population must be at least 10 times larger than the sample size. Right? And then our sampling distribution for x bar, remember that's our sample mean, right, is n, and then we have mu, comma, sigma divided by the square root of n. Right? So that's what we're going to look at and use in the next couple of examples where we are going to look at applying and using our central limit theorem.